All right, what up, everybody? Welcome back to Structure Free Learning. And in this video, we're going to talk about Poisson's ratio. In particular, I'm going to describe Poisson's effect and then explain what Poisson's ratio is. And in order to do this, the first thing we're going to do is consider an axially loaded rod. And this rod will have a circular cross section that looks like this. And it'll be loaded right through the center line. So here I'll say it had some external load, call that P, and being in equilibrium, boom, P here as well. All right, so let's say here's my axially loaded rod, and let's just go ahead and say it has a circular cross section, although I'm not really good at drawing that circular cross section here, but this is from the side view. And when we apply this axial load, we know that this thing is going to elongate. So the deformation is gonna elongate or get longer in that loaded axial direction, and it's gonna contract in this vertical or this lateral dimension. So here, you could do this by pulling a rubber band or taking your arms above your head and stretching and seeing your waist get thinner as you look younger and fitter. Anyway, so here, the deformed shape might look something like this. And if I were to observe or look at the cross section, so if I looked as an observer standing here looking this way, the cross section that I would see for this circular axially loaded rod, so this would be my original cross section. I would see that the lateral dimensions have all contracted. And what's more is that if I had the initial and final dimensions through some sensor or if I measured it with a ruler or something that was accurate enough or close enough to at least the sensitivity I wanted, I could calculate the strain. Right? So if I knew the initial length and then the final length or the deformation of this thing, and if I knew the initial height of the cross section, say the initial diameter, I knew the final diameter or just this change. And knowing these dimensions, I could calculate the final length or the final diameter, compare it to the original length and the original diameter, and then calculate essentially the longitudinal strain and the lateral strain. And this lateral strain would be a contraction, so it would be a negative strain. The final diameter would be smaller than the original diameter. What Poisson observed is that for different materials, and in fact, if the materials were isotropic, homogeneous, and we were in the linear elastic region, he observed that the ratio between the lateral and the longitudinal strain was equal to some constant. And this is the Poisson's effect. And he noticed that if you had elongation in the axial direction, that there was contraction in the lateral dimensions. If you applied compression in the longitudinal direction, then you had elongation in the lateral direction. And what Poisson observed was that the ratio of the lateral to the longitudinal normal strain was equal to some constant. And this constant is what we call Poisson's ratio. We use the symbol, the Greek letter nu, to describe it. Nu, this is equal to the negative of the lateral normal strain to the longitudinal. And most materials, when you elongate it, the lateral dimensions will contract. And when you compress it, the lateral dimensions will elongate. And here, in general, the Poisson's ratio, it's a material property. It's characteristic of a material, whether it's steel, aluminum, concrete, whatever it is. And in general, most materials, the Poisson's ratio is between 0 and 0.5. So, for example, steel has a nu of approximately 0.3, and concrete has a Poisson's ratio around somewhere between 0.1 and 0.2. So I'll say around 0.15. And cork has a Poisson's ratio that's almost 0. That's nearly 0. So basically what that's saying is that when you compress it, the lateral dimension doesn't expand. And when you pull on it, the lateral dimension does not contract. And then there's a whole nother class of materials or things like some special foams that have a negative Poisson's ratio, which means that when you pull on it, the lateral dimension actually expands. Right? That's pretty cool and has some unique applications.
All right, so I hope that was a useful introduction to Poisson's ratio. Take it easy. Structure free.